Okay, I guess we can get started. I think it's fitting that the final phase of the Pioneer Venus Orbiter mission has produced some exciting results. For those of you who didn't get them, we have a release summarizing those results, press kit, photos, and videotape with good animation. That's all available out in the lobby. This briefing will be on NASA Select, hopefully within the next 24 hours. The exact timing hasn't been determined, and we'll be putting out something giving that time. You can get the briefing on audio, and there are some press from the East Coast that will be listening in. Because of this, when the question and answer period begins, please wait to be recognized. Please wait for the mic, and please identify yourself and your organization before asking questions. The participants today are Richard Fimmel from NASA Ames, Pioneer Project Manager, Dr. David Okerson, Program Engineer from NASA Headquarters, Dr. Thomas Donohue from the University of Michigan, and also the head of the Science Steering Group for Pioneer Venus, Dr. Robert Strangeway from UCLA, Dr. Lawrence Colin from San Jose State University, and Larry is also Pioneer Project Scientist, Larry Brace from Goddard Space Flight Center and the University of Michigan, and Gerald Keating from NASA Langley Research Center. Okay, we'll begin with Richard and David, and then Larry is going to introduce some of the investigators who are in the audience and will be available to answer questions. Richard?
Good morning. Earth's twin planet, Venus, has always fascinated mankind. It's also our most explored planet. The Pioneer 12 and 13 spacecraft, the Venus Orbiter and Multiprobe, the last two of the Pioneer series, were sent to Venus to explore our evening star. The orbiter was launched in May of 1978 and arrived at Venus 5.5 months later on the 5th of December. This was followed by the Multiprobe, which was launched the 8th of August and arrived 5 days after the orbiter got there. The Earth's motion and proximity to Venus helped it get there faster. On the 9th of December, and the probes were deployed to make their measurements. The orbiter spacecraft was originally required to last 8 to 14 months. We believe it's done quite well in exceeding this by lasting over 14 years. The orbiter mission, as most of you know, ended in October this past year on the 8th when it entered the atmosphere of Venus for eventual destruction in the atmosphere. To achieve the objectives at Venus, the orbiter carried 12 science instruments, and the Multiprobe carried 18. There were 2 on the bus, 3 on each of the small probes, and 7 on the large probe, a total of 30 instruments, actually. The total mission cost to date is just slightly over $200 million. We feel that the Pioneer Venus mission has been tremendously productive and one of NASA's most economical in terms of the scientific data return for the taxpayer dollars invested. And I believe NASA can take pride in the achievements of this mission. David Okerson, a program engineer supporting Pioneer missions at headquarters, will be next.
Thank you, Richard. Venus has always drawn our attention as the most brilliant of the planets, spectacular now in the evening and soon in the morning sky. It's the planet the most like Earth in size, its composition, and distance from the sun. It's the nearest planet and thus, in many ways, the one which, by exploring, can help us best to understand the secrets of our own planet, Earth. In part because of that, NASA and the former Soviet Union have sent more spacecraft to Venus than to any other planet. Pioneer Venus, the mission which Richard just described, is the latest in a series of Pioneer missions operated by NASA's Ames Research Center. It started the process of detailed exploration of Venus after the initial reconnaissance from earlier flyby missions, and it set the stage for subsequent NASA missions to Venus, such as the Magellan mission, to explore facets of the planet in even greater detail. Pioneer Venus consisted of two spacecraft, the probes and the orbiter. The probes sent 4 different buses down through the atmosphere, whereas the orbiter was able to photograph the planet, to map its surface with radar, and to measure its high atmosphere and the interaction of the solar wind. After almost 14 years in operation, the Pioneer Venus orbiter has finished its data collection. The project is now completing its initial scientific analysis of the data and is carefully putting all of the data into the archives for use by subsequent investigators. Today, we are going to learn some of the most exciting results from the Pioneer Venus mission, ranging from reassessment of data collected by the probes 14 years ago to the latest data returned by the orbiter as it entered Venus's atmosphere last October. We now have, thanks to the Pioneer Venus mission, more information about Venus than about any other planet. It's been a fascinating mission of discovery and one which will continue to excite scientists for many years to come. Thank you.
Okay, I'd like to say a few introductory comments before introducing the gentleman in the audience. As was stated on October the 8th, when the spacecraft descended into the Venus atmosphere, it ended 14 years of data collection for a PVO. It also ended 24 years, the anniversary of 24 years in which the project has been in existence. It actually began in 1972 here at Ames Research Center. And the books won't be closed on the project until October of this year. Each of the scientists have been given an extended stay of execution here to allow them to analyze all the data in all its gory details up until the end of September of this year, and at that time the books will be closed. In a sense closed. All of the data that has been collected and the results will be archived in NASA archives and will be available to a whole new generation of scientists who can look at this Venus data. We have had the principal investigators, we've had interdisciplinary scientists, we've had guest investigators all along during this program, and NASA headquarters has instituted a new Venus data analysis program to allow other scientists to come in, relook at old data, and also to look at lots of data which I'm sure will not have been looked at by October of this year. Well, what happened on October 8th? As you can read in your kit, we ran out of fuel. Well, what was the significance of that? The significance is that Venus being so close to the sun, solar gravity has an effect on the orbit around Venus. Unlike the orbit around the Earth or planets further from the sun than is Earth, an orbiter around Venus or even an orbiter around Mercury, if we had one, would be strongly affected by, its orbit parameters would be affected by solar gravity. We have to be aware of that. This is all predictable, and one can use fuel to adjust the orbit to maintain the orbit in a fashion that it does not enter into the atmosphere, which it would if there was not this fuel to correct the orbit. We saved enough fuel from the beginning of the mission to do this at the end of the mission. We knew we had a limited amount of fuel. We were hoping we were going to last until December of last year, but we ran out of fuel in October, on October the 8th. That was not a great surprise. We didn't have a very good measure of how much fuel remained at the bottom of the tank. It's like driving your own automobile. You're not really sure. You don't wait for the last sniff, well, most of us, to go to the gas station. We don't know how our tanks perform at the lowest levels. What happened during the last few months when we were using the remaining fuel? I believe we started to use the fuel I can't remember the date, a few months before, in August it was, before, and continually used the fuel every 4 or 5 days to adjust the altitude. We took much greater risks than we took during the early part of the mission in allowing the spacecraft to go to as deep in the atmosphere as we would allow it to go to assure getting data at the low altitudes, but at the same time not allowing the spacecraft to go in far enough to burn up. This was touch and go situation because we didn't really know. We were sampling this atmosphere. We were trying to learn what this atmosphere was, but yet even using this to predict what would happen to the spacecraft. So the bottom line is that there were many orbits that the spacecraft dipped far below the altitudes which were achieved at the beginning of the mission when we were a little risk averse in terms of going to low altitudes. In the audience, in addition to the scientists who are up here, and they're down there because there's no room in the inn up here, is Paul Cloutier from Rice University. Paul, if you could just stand up and look in the camera, they can take your picture. Paul is the principal investigator for the ion mass spectrometer on the spacecraft. Which looked at the ionosphere, and one of the most notable things that happened during this last phase is that we finally got measurements down to the peak of the ionosphere and then even that below. Before, we could only predict. We never did get to the peak. We could only predict what happened below. And if you have any questions about the ionosphere, around the ionospheric peak, Paul Cloutier is the person to direct your attention to. Other person in the audience sitting next to him is Dick Hartle, who is a co-investigator on the neutral mass spectrometer experiment from Goddard Space Flight. Is he not? You're shaking your head? I guess he's the investigator on IMS, but you're also an associate of Hasso Niemann, who's the principal investigator on the Northern. They don't allow you to make even little errors up here on the neutral mass spectrometer. The same way the ion mass spectrometer measured the ions down below the peak, the neutral mass spectrometer was able to get to lower altitudes we ever got before, and in fact got into the CO2, the carbon dioxide dominated atmosphere, which exists at the very lowest. You all know that Venus is basically carbon dioxide. Its atmosphere is basically carbon dioxide, but that's only up to a certain altitude above which lighter ions begin to predominate. And during the early part of the mission, we lots of measurements of the lighter ions, and now we were able to close the gap, so to speak, with the lower atmosphere measurements by getting down low enough. And Dick is the person to ask if you'd like further information on neutral mass spectrometer. Bill Knudsen, who now works for his own company. He started out in Lockheed when this all began 108 years ago. Bill is the principal investigator on the retarding potential analyzer, which is another device which measures the ionosphere of the Earth, particularly the ion species and the temperatures in the upper atmosphere, and Bill would be the person to speak to there. Then, sitting back in the third row, he came in late, so he didn't get the honor of sitting up front, is Aaron Barnes from the plasma analyzer experiment, which is one of the key solar wind interaction experiments with the planets, and that would be the person to address any questions regarding the solar wind, although several people up here will make reference to that also. So, without further ado, let me go to Tom Donohue, who will give you his results.
Thank you, Larry. The Pioneer Venus probe neutral mass spectrometer, long time ago, 1978, revealed that Venus is a very, very dry planet. And those measurements have been confirmed since then by observations made from Earth by ground-based spectroscopic instruments that show that Venus has less water than Earth by a factor of about 100,000. One of the major questions that we address is why Venus, which ought to be a planet twin of the Earth, is so different in this important regard. The issues are, is this present small amount of water on Venus the remnant of a rather rich endowment of water that the planet might have had billions of years ago, or has the planet always been essentially dry and the water is simply injected occasionally by a comet that happens to impact the planet? Well, this same probe instrument, the neutral mass spectrometer, provided a key element in the answer to that question by revealing that heavy hydrogen, the species of hydrogen gas that is a part of the water molecule, is enriched on Venus by a factor of 150 compared to its ratio to ordinary hydrogen on any other solar system object. Earth, Comet Halley, Jupiter. Venus is completely different in being so heavily endowed with this heavy hydrogen, and that endowment is a signature we've been looking for escape of light gases from the planet. This means that since the heavier version of hydrogen is inhibited compared to the light version from escaping from the planet, there once was at least 150 times as much water on Venus as there is today. Now, 150 times is not an awful lot of water. It's only a half a meter or so, but notice I said at least. Now, during the entry phase last fall, a couple of very important things occurred. We discovered, for one thing, that the ionosphere virtually disappears and escape of gases from the planet stops during times of low solar activity, which characterized the situation during entry. And that means the time scales for establishment of a steady state with incoming comets was lengthened considerably. Equally important was work done by my colleague Dick Hartle, whom you've seen a little bit earlier here, and Joe Grabowski from NASA Goddard Space Flight Center, that revealed the existence of a very important new escape mechanism on the basis of Pioneer data that doesn't discriminate severely against escape of the heavier hydrogen. And that means you had to get to the present situation, you had to have a lot more water than 150 times. In fact, it's more like 400 times. And that means that these data indicate that Venus once had, at something between 8 and 25 meters reduced to liquid water over the surface, which is quite a bit of water. Furthermore, this escape mechanism that doesn't discriminate against deuterium means that the idea of cometary impacts supplying water to Venus is no longer tenable, because whatever object it is that might be supplying water to the planet right now could only differ in deuterium to hydrogen ratio by a factor of about 7, and comets differ by factors of 1,000. So we come to the conclusion that the data indicate that Venus was once a pretty wet planet. Does this mean that Venus once had oceans? Well, it makes it very, very likely. It makes it very likely that Venus and Earth both were formed with a lot of liquid water, Venus probably with the equivalent of a full terrestrial ocean, 4.5 billion years ago, when the sun was much less luminous than it is today, and conditions on Venus could tolerate liquid water until the sun got brighter, the surface got hotter, the water turned to steam, and the hydrogen dominated the upper atmosphere of the planet, and solar ultraviolet radiation drove this water away until we got down to the state of 8 to 25 meters, which we infer from the Pioneer Venus measurements. So that's the bottom line on our interpretation of data acquired by Pioneer Venus that relates to the question of whether Venus once had a lot of water and perhaps even an ocean. Thank you.
We'll take a few questions now. And, Keith,
I hate to jump right.
please identify yourself.
Oh, sorry, Keith Davidson, San Francisco Examiner. I hate to jump right to the most science fiction speculation, but if you have oceans up to conceivably 75 feet deep, then could the oceans have been around long enough for primitive life forms to evolve based on what we know about the origins of life on primitive Earth?
Well, the time required to work down from 20, 35 meters of water to the present very dry planet is, from what we understand of present escape mechanisms, could be less than 3 billion years or that order. So it's entirely conceivable that liquid water existed on the surface of Venus 4 times as long as 1 billion years or so. And we know that in the case of Earth, this was long enough for life to develop. And so, you know, I'm not reticent about answering your science fiction question. If there was liquid water, if the water was in the form of liquid, and we can't prove that from our data, and if it lasted for as long as 1 billion years, then by analogy with the Earth, primitive life forms could have evolved.
Based on what we know about the geological history of Venus, could conceivably any fossil relics of these life forms have survived long enough so that they might be detectable by robot probes?
No, because Magellan has clearly revealed that the surface of Venus has that the then surface has been covered deeply by lava flows. The planet was last resurfaced somewhere between 200 million and 500 million years ago, but all traces of that early surface have probably been obliterated.
Evan Rosen, KICU Television. If you're to step back from these findings and kind of look at the biggest of big pictures, what is the significance of all this water being on Venus, so much more than originally was expected? In terms of what you know about planets in general, about Earth and how it was formed, what's the big picture significance of this research?
Well, it does. It tends to confirm the picture that we have now about the way the planets were formed by 4.6 billion years ago, which says that everything started with a spinning nebula of dust and gas, and the little pieces of dust collided with each other and grew into boulders and grew and grew and grew by collision with each other, finally ending up with great big objects such as Venus, Earth, Mars, Mercury, and the outer planets. This picture says there really shouldn't be any difference between, as far as composition is concerned, among the terrestrial planets. They ought to be the same as far as composition is concerned. And so a mystery of why Venus appears to be different now in composition is resolved if we can conclude that, well, in the beginning, Venus did have as much hydrogen and oxygen as the Earth had. And you know, you can make the same argument about Mars, that if Mars were only as big as Earth, it probably would be like Earth today.
In following up, for you, what's the most useful aspect of the information you've been able to gather? How will it be useful to you now and in the future?
Useful, it would be useful to me because it makes me easier to get grants approved. But I think it's useful to humanity in general in that it's a confidence-building measure in our understanding of the physics that goes into that's involved in the formation of the planets. It means that we're more confident that we understand what's going on Earth, this understanding of the other planets does enhance our confidence that we know what's happening on our planet.
Yeah.
Charlie Pettit, San Francisco Chronicle. What is the ratio between deuterium and hydrogen you're finding on Venus? And more interestingly, at what point did you actually make these measurements of deuterium? Did you see that like on the last orbit before the thing flamed out, or weeks before that, and at what altitude and what instrument was it? I mean, is this real late in the going, or was it something that built up for several months?
This was really early in the going. Both the orbiter and the probe obtained data indicating that deuterium was much more abundant on Venus than they were on the Earth. The neutral mass spectrometer on the large probe that entered the atmosphere in December of '78 obtained the essential information that water on Venus that we sampled because sulfuric acid droplets collected on the inlet to the neutral mass spectrometer. We analyzed that water, and we found the ratio of HDO to H2O to be higher by a factor of 150 than it is on Earth. This ratio is 5% for Venus. It's 3.2 times 10 to the minus 4 on Earth. That's a big factor. In the meanwhile, the orbiter ion mass spectrometer that Paul is the PI on was obtaining information about ions of mass 2 in the upper atmosphere. At first, it was thought that those ions were H2 molecular ions. But work that Dick Hartle did and others of our colleagues showed that the idea that these were molecular ions was not tenable, and they had to be deuterium ions. And the ratio they got from their analysis was also 150 or so. Then after that, and that was a long time ago, after that, people using ground-based telescopes or telescopes on the Kuiper aircraft, looking at Venus in the infrared, looking at water vapor lines and HDO lines, found the same ratio. So this is information that's been around for a long time. What we found on the very recently was this new mechanism for escape that Dick Hartle and Joe Grabowski turned up, and also the revelation that the ionospheric ions get so tenuous during times of low solar activity that escape is turned off. It's a long-winded answer, but that's the history of what happened.
Yeah.
Of Reuters. Does this tell you anything about the future of the Earth, such as the oceans could at some stage dry up on the Earth?
This in itself doesn't tell us that, but in fact, the study of the processes of, especially the process of the runaway greenhouse, which is the process that occurs when the oceans evaporated on Venus and hydrogen went away, by people like Jim Casting and Jim Pollock, both of whom were at Ames, or Jim Casting was at Ames at that time, and Jim Pollock still is. Those studies of the runaway greenhouse clearly indicate that could never happen at Earth. Earth is too far away from the sun. Never, I mean, for billions of years. The sun's going to have to get an awful lot brighter before that happens. We're in no danger of causing a runaway greenhouse on Earth merely by burning fossil fuels. We're not going to, I mean, things are bad enough, will be bad enough for Earth because of increased CO2 and because of the greenhouse effect. But the dire thing, such as turning Earth into Venus, is not something we have to be concerned about.
John Andrews with AP. I have two questions. In answering the question on could there have been life on Venus, you made you used the phrase "if water was in the form of liquid." Could you expound on that a little? I thought water was liquid, and if you're talking about oceans that weren't liquid oceans, what are you referring to?
No, I mean,
And I have a
water need not be in the liquid phase. Water can be vapor. It is conceivable that that the planet was so hot, not because the sun was bright, but because there's a lot of heat generated during accretion, that this water never condensed into the liquid phase, but was always in the form of steam. So if the atmosphere is very warm and the water that I talk about, this early, fairly rich endowment, was in the form of steam in the atmosphere, conditions are so different than they were on early Earth that I can't use the analogy with early Earth to suggest that it's feasible that life existed. It's a question of what phase the water was in. Was it liquid or was it vapor?
My second question, how much of the material that you're presenting today is reanalyzed material from earlier findings, and how much is material that was gathered and sent back in the last few months of the orbit?
The data that deal with the very, very low rate of escape, and that's very important data, were obtained during the last couple of months of life of the orbiter. The other, the analysis that Hartle and Grabowski did that show this important source of loss of hydrogen ions and deuterium ions was analysis done very recently, last summer, but done on data acquired much earlier during the first 3 seasons.
Earlier, Marla Miller, KNTV, San Jose. You said earlier that you refused to rule out primitive life forms. Can you describe what they might have looked like?
Mushrooms.
Nothing.
The answer is no.
No, yeah, the answer,
Oh, well, okay,
no.
what you might have suspected they might have looked like.
Well, the earliest form, the earliest fossils on Earth are objects called stromatolites. You know, they're very primitive mats that you find on seashores. They still exist, but there are fossil stromatolites found in places like Australia, and again, by analogy, I can say, well, it might have been something like that, but I don't know.
I have 2 questions. Glenda Chu from San Jose Mercury. I have 2 questions. One is, do we know anything about what the temperatures might have been like back then when there was water? Do we know anything from the geology or the chemistry or anything that would give you a good guess about whether this water was in the form of vapor or not? And I'm assuming it couldn't have been in the form of ice since it's so much warmer there, but
Right.
I don't know.
Well, we're pretty sure about the question of how luminous the sun was, because we can look at other stars like the sun in the universe, and there are whole lots of them that are like the sun. Some of them just formed, some are more mature, and so this assertion that the sun was 70% as bright 4.5 billion years ago is on good solid footing, and you can. It's an easy matter of physics to then determine how what the surface temperature of Venus would have been, although it does depend on how much water vapor and how much carbon dioxide, how much greenhouse effect there was. But a reasonable figure is somewhere in the neighborhood of 50 or 60, 70, well, more like 70 or 80 degrees Fahrenheit, a little bit warmer than the present terrestrial terrestrial surface temperature. Not a lot warmer. That's the simplest. That's the result of the simplest kind of exercise that you can do. But it is possible that the surface was quite warm because of a lot of heat was generated when these planets were being formed by impact of planetesimals with each other. And that's true of the Earth as well. We're just not really sure about what conditions were on Earth during the first several hundred million years, but we know that on Earth the temperature was reduced and things settled down, that we had oceans, because we know that 3.8 billion years ago there were sedimentary rocks on Earth. So sedimentary rocks means there has to be time for sediments to form, and we're only 700 million years away from the beginning. So as far as Earth is concerned, we did have liquid water quite early, and there isn't there's no reason to exclude that for Venus.
My other question is, several people mentioned that there's been a lot of reanalysis of older data going on, and I wondered, aside from the hydrogen escape stuff that you've already talked about, if there is other data from back early on that people have found renewed interest in and maybe are reinterpreting, and what that might be.
We're still looking at early data, both from the probe and from the neutral mass spectrometer. I know that I'm spending a lot of my time still trying to understand data that we obtained with the neutral mass spectrometer relating to the existence of stuff like methane and hydrogen gas and helium. Some of these data are very, very difficult to interpret. They take a lot of time, and you do a lot of other things and come back to the data occasionally. So that I'm reworking the neutral mass spectrometer data, and there are stories about methane on the discovered by the neutral mass spectrometer that have got some of our attention. Has got some attention lately, and I guess my colleagues would speak for themselves, but the orbiter data relating to the neutral atmosphere and the ionosphere is still rich, and in data that hasn't been completely analyzed, and we've got new ways of looking at it in the light of the information we got, which was somewhat surprising to most of us during the reentry phase. This has caused us to go back and compare stuff we're looking at now with conditions that existed then.
If I could just make a...
I have one quick question.
I was going to... all right, we're going to have your question and one more about oceans, and then finish off the rest of the presentations. Go ahead.
What is it more that you want to know? The books will be closed on this apparently in October. What argument would you use from here for future funding to try to get another mission? What more do you want to know with what you've gained here in the last several months?
Well, in the first place, the data analysis funding will not end in October. The direct funding of the principal investigators by the project will terminate then, but there is a Venus data analysis program that's funded by NASA headquarters for the next 3 years, and there are other ways of getting funding to study the data that will allow us to work on the data for a long time to come, I hope. There are a lot of issues that were raised by Pioneer Venus that need to be addressed, a lot of things we don't know about the planet that I could go into, such as what is the redox state, how does the surface of the interaction between the atmosphere and the surface of Venus determine the present chemistry of the atmosphere? How does that result in the formation of the sulfuric acid clouds around Venus? There are questions that have to do with the implications of the noble gas inventory of the planet that we discovered with Pioneer Venus for the way the planets acquired their volatiles. All of these cry out for return to Venus over and over again with a lot of small missions that are focused to answer questions that have been raised by both Pioneer Venus and by Magellan. And it is encouraging that the Space Agency has begun a program of small missions called Discovery that I hope will allow us to address these very important issues that have been that resulted from the PV orbiter and probe mission.
Tony?
in San Francisco. If Venus had liquid water, would it have any exposed land masses? Can you talk about that at all?
Would it have had exposed land mass? Oh, no way of knowing. I have no way of knowing. In fact, during those early the times on Earth, the amount of continental crust was very, very small. Most interpretation or most the present understanding of Earth is that during that epoch there wasn't much continental crust. That the globe was mostly covered by oceans. So it's probable that there weren't any big continents.
Okay, Bob, you want to?
Well, lightning is observed in many. I'm going to talk about the evidence for lightning on Venus. And the thing is, lightning is observed in many planets within the solar system. And of course, while visual observations are the most conclusive evidence for lightning, radio waves, which is what I'm involved in, can also be used as a remote sensor for lightning. As an example, radio waves detected by the Voyager spacecraft has been cited as evidence for lightning at the outer planets such as Saturn and Neptune. And indeed, the Orbiter Electric Field Detector, which is the plasma wave instrument, was included as part of the Pioneer Venus instrument complement to search for plasma waves generated by lightning, in addition to some other work that I'm not going to talk about. Well, why are we concerned whether or not lightning occurs on Venus? First of all, a sufficiently high rate of lightning can significantly modify atmospheric chemistry. And as an example, terrestrial lightning dissipates about 1 billion watts per lightning strike, and roughly 100 flashes per second occur on the Earth. That's an awful lot of energy to be dumping into the atmosphere. Lastly, the presence of lightning on Venus raises questions concerning atmospheric electricity. In particular, for Venus, can sulfuric acid clouds, as opposed to water clouds, can sulfuric acid clouds in a carbon dioxide atmosphere charge like water clouds in air, which is, of course, what we're familiar with the Earth. And early in the Pioneer Venus mission, plasma wave bursts were detected at low altitudes in the night-side ionosphere, and these waves were attributed to lightning. Originally, it was thought that lightning was a signature of active volcanism, but that theory is not generally accepted now. Rather, it appears that lightning, if it occurs, is generated near the dusk local time sector, suggesting that strong atmospheric convection occurs there. However, it should be noted that lightning interpretation for the plasma wave signatures that I'm involved with is not universally accepted within the community, the scientific community. And let me explain both the hypothesis and a little bit more of the issues arising out of this from the sketch that's to my left on over there. Basically, the Pioneer Venus orbiter probed early in the mission above the ionosphere, which is the green region there. And so we detected radio waves in regions known as holes where there's a strong magnetic field and a reduced ionospheric density. The ionosphere tends to shield waves from the atmosphere. So you need to have a reduced density in the ionosphere for the waves to escape and a strong field to guide the waves out of the ionosphere. This is where Pioneer Venus observed these waves. However, what we didn't know is whether the magnetic field itself penetrated the ionosphere or was shielded completely from the planet by the ionosphere. And moreover, we didn't really know if the radio waves were generated in the atmosphere itself. We've assumed so, that's why we said there's lightning there, but what we would like as part of the entry phase was to detect in the atmosphere itself, below the ionosphere, the signals that we think are due to lightning. So one of the things that was very exciting about the entry phase data is that we did indeed go below the ionospheric density peak. This has been confirmed by the particle instruments. And we also found that in these late orbits, that the field in the ionosphere, magnetic field that is, can be very strong. This is work by Christopher Russell from UCLA, who was the principal investigator on the magnetometer. He reports that strong fields were detected in various regions throughout the night-side ionosphere, such as we require for these waves to escape. And secondly, the last orbit of the Pioneer Venus orbiter showed intense waves at lowest altitude, right where we'd expect them to be if lightning occurred. So those of us who think that lightning does occur on Venus do have confirming evidence from the entry phase data to suggest that there is a strong, persistent source of lightning in the atmosphere. But I should close by noting that this is by no means a universally accepted hypothesis and is still being debated within the scientific community. Thank you.
Larry?
Got a question there.
Well, I want to hold the questions until we get the other two presentations.
Yeah.
Larry Briggs.
Okay. The couple of issues, a couple of ways of looking at the study of the atmosphere at Venus. One of them is the question of solar-wind interactions with planetary bodies. You've seen pictures of comets, and you see how the tail rays of the comets point away from the sun. That's because the atmosphere of the sun is expanding out at very high velocities and interacting with the body. In the case of a comet, it's primarily ice, solid water, and that interaction allows the solar wind to get right into the surface of the comet, and the solar light and heat evaporates that material, and it causes a big ball of gas which the comet interacts, or which the solar wind interacts with. In the case of a solid planet, it depends very much on whether the planet has an atmosphere, or whether the planet has a magnetic field. And we've looked closely over the years at the interaction of the solar wind with the Earth, which is a highly magnetized planet that, because of its magnetic field, stands off the solar wind and keeps the solar wind from coming into the atmosphere of the planet, and the ionosphere, which is part of the upper part, is part of the upper part of the atmosphere. And we're fairly familiar with what the effects are there, how the solar wind produces energization of particles within the magnetosphere, and those particles are dumped into the atmosphere at high latitudes to create the aurora, and currents flowing in the current system around the Earth that cause interruption of communications and power, etc. So there's some practical effects on Earth. Venus was interesting to us. The solar wind interaction with the ionosphere of Venus was interesting because Venus doesn't have a magnetic field, or at least not a measurable one so far. Very weak magnetic field, if any. And that allows the solar wind to come right down in contact with the atmosphere, including the ionosphere. And that's some new physics that we haven't been able to measure directly before. And I wanted to stand up here. Is this microphone working? We have to. There were some questions about the old data versus the new data. We haven't known about Venus for 4.5 billion years, so all of the data is new, and it's all different because the early data were taken at solar maximum when the ionosphere, we think, looks something like this. It was very large. It went out to 1,000 kilometers here and several thousand kilometers downstream, and at least 300 or 400 kilometers out in front. But the solar cycle is only 11 years, and so that the data we got during entry looked at the ionosphere under a different condition when there was only half as much ultraviolet and extreme ultraviolet radiation from the sun to create the ionosphere. And with a weaker ionosphere that we had during the entry period, because it was solar minimum, or approaching solar minimum, it was less able to resist these fluxes of hot hydrogen ions flowing from the sun. And the ionosphere was pushed down rather close to the planet. As Tom Donohue mentioned, this upper portion was almost completely removed. And that was very interesting because at times back at solar maximum when we had a strong ionosphere, but the solar wind was unusually strong on some days. Some kind of solar storm that brought a lot of particles to Venus also removed the top of the atmosphere, and it looked very much like it does nearly all the time at solar minimum, what we saw last fall. And so that's why we go back and look at the old data. We see something that occurred almost continuously during the entry period at solar minimum. We saw it a few times. I heard the number a day or so ago, maybe only 8 or 9 times out of the hundreds of orbits that we got back in 1979 and 80. Some of these features here look familiar if you're familiar with comets. We call these tail rays, in analogous to what are seen photographically in ion emissions from a comet. The scale of this is much smaller than a comet. A comet is 1,000 times bigger than this. Although its nucleus may only be a few kilometers across, whereas Venus is 6,000 kilometers in radius. The significance of all of this is the question of what happens to that ionization. Why, when it's removed, as it is at solar minimum or at times of high solar wind pressure, what happens to it? Does that really mean that the escape rate of ionization is less? And maybe it's more. Where did they go? Maybe they're removed somewhere else, and for that reason they're not seen here. And it doesn't necessarily mean the escape rate is lower because there's not much here to escape. It may be escaping from somewhere else. I just wanted to answer that question as to the interpretation of the solar minimum data. I think it isn't clear what that means in terms of escape rate, and you realize that escape rate is important because that's one way to remove some of the atmosphere, and over a long period of time that can have an effect on the remaining atmosphere, how much there is left of it. Thank you very much.
Jerry?
Hi, I'm Jerry Keating from NASA Langley Research Center. I'm principal investigator on the orbiter atmospheric drag experiment. And essentially what we do is we see how the orbit decays, how it shrinks, and how the period of the satellite decreases with time. And from that we can determine densities in the vicinity of its closest approach to the planet, called the periapsis point. And then by studying how the density varies with altitude, but with the periapsis variations in altitude, we can get vertical structure and infer composition and temperature. During the entry phase of the mission, I show here a schematic of what how the periapsis altitude varied as a function of time. And we see here, this is the local solar time. So this is near the terminator, and then we're going into the night side of the planet. And here is the altitude of periapsis. And so when we dropped down to low altitude levels from the orbiter atmospheric drag experiment, we could determine that we were close to where we get into trouble with aerodynamic heating. And so from those atmospheric drag measurements, then we would decide to kick the periapsis altitude up to higher altitudes, and then it would naturally start to drop again. And so we could decide with that experiment how to pull out before we burned up. And in this way, we were able to make measurements down at very, very low altitudes on the night side of the planet. I have another figure here that shows you some of the things that we've learned here with the atmospheric drag experiment, along with the orbiter neutral mass spectrometer experiment, another experiment aboard the Pioneer Venus spacecraft. And what we see here is a comparison of Earth and our sister planet Venus. You can see a lot of differences here between the two planets, even though they're the same size, and Venus is somewhat closer to the sun than the Earth. So we see here temperature 0 to, I mean, this is altitude 0 to 300 kilometers. This is near 200 miles. And then temperature in Kelvin, 273 Kelvin is 0 centigrade or freezing. So this gives you some idea of the differences here. Of course, at the surface of Venus, extraordinarily hot, it will melt lead. And then when you get up into this region of the atmosphere where we've been making these measurements, it's very, very cold. And the night side, 100 Kelvin, day side, 300 Kelvin, or near room temperature. However, the Earth is very, very hot compared to Venus, 1,000 Kelvin up in the thermosphere, and then much cooler than Venus at the surface. A lot of this has to do with the fact that Venus has a CO2 atmosphere. We proposed that the very, very cold temperatures on the day side of Venus, this is called the thermosphere, that those temperatures, the reason they were so cold, is that there's very strong radiative cooling of CO2, atomic oxygen exciting CO2 into very, very strong radiative cooling. We predicted that if this were true, that we would have a very weak 11-year solar activity variation of the atmosphere at these levels, and we found that was the case. So it looks like that the CO2 cooling, atomic oxygen exciting CO2 into extraordinary strong emission is affecting the upper atmosphere of Venus, and probably will also affect other planets like the Earth. If we double CO2 in the next century, we should start seeing cooling of the upper atmosphere, the thermosphere of the Earth, and of course other effects down at the surface, which have been discussed before, but we may have a very strong effect in the upper atmosphere. I'd like to, one other thing I want to show here, this is the cryosphere, where the temperature is actually dropping with altitude. This is probably the only place in the solar system where this property occurs, and so we had to call it something other than a thermosphere like we have on the Earth, cryosphere, and so we've detected that with the with these measurements. So this briefly describes the different things that we've learned during the entry phase. First, we found densities that are much higher than what we expected up in the exosphere. This is even higher altitudes, up at 350 kilometers. We can't really talk about temperatures up there, but we can talk about increased densities. Temperatures are a Maxwellian property. You have to have a Maxwellian distribution of species. You don't have that up in the exosphere. But anyway, we can talk about the high densities up there. We found a colder cryosphere, temperatures probably minimizing around 140 kilometers. And then I've already mentioned the weak solar cycle effects and this very strong radiative cooling. Thank you.
Do you think that your findings presented today will promote the study of whether or not life existed in some form on Venus? Is that a new door?
Well, let me back up now and do my best to caution you that that we found certain things and can infer a certain amount of water, 8 to 35 meters of water some long time ago. I don't know whether that was 3 billion years ago or 3.5 billion years ago or 4.5 billion years ago. I know that there is no strong reason to exclude it being as recently as 3.5 billion years ago. But let's be very careful that I am talking about speculation beyond what we actually can measure. I think these the evidence that there probably was as much water as I talked about at one time will induce people to have a closer look at what conditions might have existed during the early times on the planet. But I doubt very much that we're ever going to be in a position to close the circle, to find in the present solar system evidence that this situation existed or did not exist. It's tough to go beyond the state we're presently in and infer with a fair certainty what the situation was early on the planet. And the planet itself has been completely altered since those days. So I've been willing to engage in speculation and to say that this could have been, that the evidence that we have does not exclude, and even stronger than that, suggests that the conditions were those that I mentioned. But we haven't proved it.
Charlie Pettit, San Francisco Chronicle. I'm a little confused about this loss question when the ocean went away. I mean, I've heard you, Dr. Donohue, say that it may be that the ionosphere was not there very much, so it took a long time. At least I think I understood that. And Larry Brace said, however, that absence of an ionosphere during quiet sun periods doesn't necessarily mean that the loss of hydrogen or deuterium was affected much. I think he said that. And I'm further confused over who all the people were who actually put together these models explaining when or how these isotopes disappeared. So could someone give me a concise summary of who said it? I've heard this name Hartle and somebody else, I don't know who they are, who apparently have been involved in this question. And I'm just confused over where the oceans went and what part of this was new that came from the late end of the Pioneer Venus lifetime.
There are a lot of actors. One of them, Dick Hartle, was introduced early, and Dick, you want to talk to Dick about the escape of hydrogen and deuterium induced by charge separation electric fields. You can do that right now.
Okay, good. And maybe you can address that and what new has changed the idea of the time scale it would take to deprive a planet of an ocean.
Well, that is certainly one, because that well, nothing has changed recently regarding the question of how long it would take for the solar ultraviolet radiation to drive away most of the water associated with an ocean. The work was done by Jim Keating and Jim Pollock here at Ames, 1983 or 84. Keating and Pollock published a couple of papers that were inspired by the early D over H results, deuterium to hydrogen results that we reported in 1982, that showed various ways in which water could be lost massively by Venus, and in the course of a couple of 100 million years. The work of Keating and Pollock revealed that you could get rid of most of the water associated with an ocean in a time of a couple of 100 million years. Now the question is, how long does it take to get from that state, when loss of most of the ocean occurs, to the present? And that does depend on details about how the present escape mechanism functions. And this is something that we're studying in the Pioneer Venus data. And this is something, our understanding of what the escape processes are that operate on the Venus that has been there since the oceans, most of the oceans were lost, if indeed they were lost, is something that we've been doing with Pioneer Venus data. And I guess Larry Brace and I are going to have a little seminar between ourselves. I don't know what Larry meant. He'll have to speak for himself. I will say that the reduction in hydrogen ion densities that we observed and the reduction in ionic densities on the day side of the planet that have been observed during solar minimum have an implication for all escape mechanisms I'm aware of that says that they've been reduced dramatically by a factor of 10 or more under reduced solar activity conditions. And so I don't know what Larry has in mind, but I don't want to get in an argument here before all of you guys with Larry. Yes.
Briefly address this escape. Yeah, I could tell you about the escape mechanism. It's very similar to one that. All right, the escape mechanism that we've worked on about a year ago is very similar to one we have understood rather well on Earth, something called the polar wind. But there is a big difference between what's going on Venus and what's going on Earth. The Earth has a very strong magnetic field, and what happens in the polar region of the Earth is that due to various balances or imbalances of pressure and gravity, the light ions escape out the polar regions out into the magnetosphere and are lost. On Venus, we have an intrinsic magnetic field. We don't have an intrinsic magnetic field, rather, it's induced. But nevertheless, it's very weak, and the ions flow right across the magnetic field, and they escape very similarly to the polar wind on Earth. Basically what it is, it's an imbalance between the gravitational pressure that holds the atmosphere down and the ions down, and the kinetic pressure, or the pressure of the atmosphere that forces them up, and the induced magnetic field also causes a weak force to force the ions up. Now the other thing is hydrogen and deuterium are escaping about at the same rate, and that is just simply due to the fact that their masses are about equal. One is just twice as massive as the other. And so the escape rates are about the same, and that's the sort of thing that Tom Donohue was referring to.
That's very, very important, because other escape mechanisms discriminate strongly against deuterium. The fact that deuterium goes away almost effectively as hydrogen does means that you had to have a lot more water early in order to get down to the present enrichment. You know, if the mechanism doesn't discriminate in much against deuterium, you need more water to get to the present state.
I'm not also sure what Larry was talking about, because as he said earlier, during solar minimum, the 1992 condition, there's considerably less ionosphere here, considerably less ionosphere to flow to the night side. In addition, the solar wind pressed this region down significantly, so it was very difficult for the ionosphere to flow back here, so that there was very little ionosphere on the top. So there was very little to escape. So I'm not sure what he was driving at. But one other interesting thing about this is that the lack of ionosphere back here surprised us in the sense that we still had a very strong main ionosphere layer down at lower altitudes. And it allowed us to study or analyze something that we always thought occurred in the past, and that is that the solar wind may be playing a role. The hot electrons that are out here playing a role in maintaining this ionosphere down here. So by pinching off this other source,
which was in a sense confusing this process, it allowed us to study the maintenance of the ionosphere on the night side. And then we can go back to our data, our earlier data, and include that source in there with some confidence.
Recently, a few geologists have speculated that Venus may have undergone a very limited form of something like plate subduction on the Earth. Is it possible that some of this primeval water might have been absorbed by the planetary crust and is still there today?
The answer is yes. It's possible that that an appreciable amount of the early water was subducted, and in fact, it's possible that it is possible that the present water has been cycled through the crust. I mean, the early water was subducted and has been cycled repeatedly through the crust and has re-entered the atmosphere as a consequence of volcanism over time, so that there's a way of looking at what's going on now that is a steady state, but one in which the water is in a steady state between escape by Dick's mechanism and others and injection of water through volcanism. But this has to be water, this injected water in a steady state has to be water that is rich in deuterium. We can't tolerate, under these conditions of easy escape of deuterium, we can't set up a steady state between deuterium poor source and escape. It just won't work. It takes too long to establish the steady state, and besides, you just can't get there from here. If you try to dump comets that have ratios of D to H of the order of a few times 10 to the minus 4 in this atmosphere and get to a ratio of a few percent with an escape mechanism that doesn't discriminate against deuterium, you obviously can't do it. And I mean, I can wave my arms and say that, but I can also calculate and show that it's impossible. So there could be a steady state involving water that was subducted early and has been coming out over and over again over time.
2 or 3 more questions. Glenda?
I don't remember hearing any comparison of how much, if there was up to 25, thanks, if there was up to 25 meters of water once on the surface of Venus, how would that compare to the amount of water now on Earth in the oceans?
Oh, well, the average, that's about a factor of 300 compared to the terrestrial liquid water. The oceans average several kilometers deep. Right? Yeah. The oceans are miles deep, so we're still not talking about oceans. 25 meters is 75 feet, so that's a modest lake, you know. But, you know, it's a planet-wide average.
Yeah, it's a lot of water.
It's a lot of water. I mean, it's a lot of water. It's very, very difficult for a reasonable person to say that, well, 75 meters and there we stop. We can make pretty strong arguments that there was as much as 75 meters several billion years ago, but because, strictly speaking, we can't say that there was more than that. But since the reasonable, the implications of all that we know about the way the solar system was formed are that Venus started out just like the Earth, within a factor of a few. The implications that indeed that's the case, and Venus had an endowment of a full terrestrial ocean or so. That's not a massive intellectual jump to make.
Don?
Don Knapp at CNN. Dr. Donohue, is there anything you learned about the last bounces of the Explorer orbiter off the atmosphere that gave you a better understanding of this escape mechanism? Is this new stuff, or are we just talking about the long analysis of old data?
The new stuff, there definitely is new stuff, and the new stuff is that the density of most ionic species, and most important from our point of view, hydrogen ions, on the night side, on the so-called dawn bulge, was reduced by factors of the order of 20 or so, 20 times fewer ions. Hydrogen ions are in that in the ionosphere, were in the ionosphere last fall than were there in 1978, in the 3 seasons. We explored that part of the ionosphere during solar maximum, and that does for all the escape mechanisms that I am aware of, this means that escape was reduced by roughly the same factor during this period, and that's essentially turning off escape, so that you cut down on the escape flux averaged over long periods of time by a factor of roughly 2, since it's on half the time and sort of off the other half of the time for hydrogen ions. So that is new, and it changes the time scales. That's what it does.
I'd just like to ask members of the panel, I'm Alan Call from NBC News. Is there anything that jumps out at you now in looking back at the data from this planet that says this planet evolved differently from Earth because of A, B, and C, or Earth evolved differently from Venus because of A, B, and C? Is there any data at all that suggests one is the way it is because, and one isn't because?
Well, there's all the data we've been talking about, the dryness of Venus, it's the fact that the carbon on Venus is in the atmosphere in the form of carbon dioxide gas, whereas on Earth it has been converted to carbonate rocks and layered down in the crust. I mean, I can continue this catalog of differences between Earth and Venus, all of which point to the importance of this planet Venus being 7/10 as far from the Earth as the Sun is. That's the big difference, and this is the entire study of Venus has, as far as evolution is concerned and similarity among planets, has led us to conclude, most of us, that the difference is that Venus is sufficiently closer to the Sun than Earth is, that the surface is so hot that water was driven away, and without water on the planet, you get carbon dioxide in the atmosphere, whereas with water on the liquid water on the planet, the carbon dioxide reacts with weathered silicate rocks and is converted to carbonates, and this makes all the difference between the two planets.
Could we add a couple of things to that? Tom has said that the major difference between Venus, if you had to take one item, the major difference between Venus and Earth is the fact that Venus is closer to the Sun. I don't want you to go away thinking that it could explain, for instance, why Mars is so much different than Venus, than Earth. Mars is different from Earth, yes, because it's further from the Sun than we are, but it's a much less massive planet. And that, of course, says a lot about the ability to hold atmospheres and escaping atmospheres. So there's an extra complication when you go to a smaller planet, whereas a planet about the same size as Earth, the distance from the Sun is the most critical item.
I also want to add something on that says that the fact that both Venus and Mars don't have very large intrinsic magnetic fields allows the solar wind to interact directly with the ionosphere, thus an additional loss mechanism supplied there. The ionosphere itself is scavenged by the solar wind. That's another way of losing part of the atmosphere. As opposed to the Earth, where the magnetic field is so large that anything that blows off the ionosphere is cycled around within the magnetosphere, and very little is lost to the solar wind directly.
So is it safe to conclude that if we're going to find life somewhere, it's going to have to be very similar to what we have on Earth? In terms of presence of water, in terms of magnetic, etc.?
That's really speculation, but Tom's shaking his head saying no, and I'm going to say yes.
Yeah, I guess it is. We don't, you know, as far as we know, water is essential, but that's as far as we know. you read science fiction and you'll find other ways to generate life, ways that are non-terrestrial. But what my colleagues have been saying about Mars is relevant to this discussion. If you were to put Earth where Mars is, a planet as big as Earth where Mars is, you would probably have a planet on which life could develop, because a planet as big as Earth wouldn't have lost all of its internal heat, and plate tectonics could still be going on. The only difference might well be that there's more carbon dioxide in the atmosphere than there is in the present atmosphere of Earth, and the greenhouse effect would have to operate to keep the temperature higher. But I can draw a scenario involving volcanism and weathering and feedbacks that show that if you put Earth out where Mars is, the planet would probably naturally readjust through a feedback mechanism to keep the temperature high enough for life to develop.
John Cox from the Sacramento Bee. Dr. Donohue, you touched on it just a moment ago. The presence of water in the early Venus has implications for the early atmosphere that would suggest a difference in a major way than what you're seeing out there with the orbiter now. You're talking about less carbon dioxide in the atmosphere?
In the
early atmosphere.
In the early, yeah, I think in the on an early Venus of the sort that one can imagine, with liquid water, weathering of silicate rocks could, but no, this of course means that there has to be some continental landmass for that to happen. There had to be some continental landmass for that to happen on Earth. But the carbon dioxide in the presence of water and rain and weathering reacts with silicates and converts them into carbonates. That's what happened on Earth, for sure, and could have happened on Venus, so that the carbon dioxide during the early times could have been sequestered in the form of carbonates and then released when the temperature increased, because the amount of CO2, the amount of carbon that is sequestered in the form of carbonates compared to the amount that's in the form of CO2 depends very much on the temperature.
Thank you very much. We have materials out in the lobby if you need them.
Venus once had a very large amount of water, perhaps as much water as there is in the ocean of the Earth. When Venus was formed, when the Earth was formed, the sun was much less bright than it is today, and so the temperature on the surface of Venus was low enough to allow water to be liquid. One of the most important discoveries of the Pioneer Venus mission was that the concentration of heavy water on Venus is much higher than it is on Earth, which means that Venus has lost a lot of water.